have heard on Monday there was a curfew in Varda district, so people were not able to get into digital Nalanda offices to begin the sessions as usual on Monday. So we'll recommence the lectures from Monday as per the usual schedule. We have since migrated to Google Classroom, and this is to give us all a chance to interact a little bit more. So this is part of what this experiment will be. I want to see how this actually works. And so I myself, I've never used Google Classroom. So I'm wondering how this will actually work. So what we will try to do today is we'll work through a problem set. So let me just see. So let's see. Okay. Sorry. Okay. So let's proceed. So I hope that well, actually, let's actually see if whether we are able to talk to each other freely. So has anybody on this call, was anybody not had not had a chance to either see the first lecture, the induction lecture and the first introductory lecture online, or did not attend? So has everybody seen, is everybody familiar with the material covered in the first lecture? If not, please just tell me. Okay, so I can presume that everybody has indeed attended the first lecture. So what we will do today is we will work. So I posted this on the problem sets. I've posted this problem set on the Google Classroom window portal, and also it'll be up on the Digital Nalanda website as well. And so, can you see my screen? Yes. Okay. Good. So let's see. So, what do I want to? Okay. So, I think I want it. Okay. So what we're going to do is work through a problem set. Okay. So can everybody see this PDF? If I can't actually, you have to unmute your microphone and tell me at this point, because I can't see the Google screen. So can everybody see this problem set in front of them on the screen? Is it possible to unmute and tell me?
Yeah, we can.
Yes, you can see. Okay, good. Okay. So well, part of what this problem set is setting out to do is first. So I'm not sure how. So as mentioned in the course, that this is not assuming any mathematical background beyond what is present at standard 10, but nevertheless we are going to do advanced stuff. All this means is that the concepts that you need are already there in your toolbox. But we are going to have to work hard to develop them into things that we really need to use for statistical analyses and information science and data science. And so a lot of the concepts that will come in very useful in, well, essential really in any analysis of data is things like estimators and likelihood functions. These are things that we briefly covered in the first lecture. We will be seeing them again. And when you start going from, let's say, this classroom into, studying things on your own in other textbooks or in literature, you will find a certain mathematical formalism that will be used all the time. And we are going to just sort of start to get used to it here. So I thought we would just warm up very quickly and work through some very simple problems. Well, they may not be simple if you've never seen them before. But so what we will do is we'll just work through a series of problem sets meant to solidify some of the concepts covered in the first class, but also to get you used to some of the notation. Okay, so the notation can be some of the trickiest part. It's a very condensed, it's a very compact way of writing certain mathematical expressions. So if you have seen them before, you will find it quite straightforward. But even if you haven't seen it before, maybe there will be some interesting problems in the later questions in this problem set that that you might find useful. So what I would like you to do now is spend a few minutes actually just going through just doing question one. Okay, so I'll give you let's say this. I'll give you 5 minutes now. Please, if you just pull out a note paper and a pen or a pencil, just try to do question one yourself, and then after 5 minutes, I will cover. I will run through the solution myself, and then we'll go through all of the. I have something like 11 questions today. So this is primarily this is meant to really just test this Google Classroom format to see how interactive it is. But also it's meant as sort of just a nice way to just make sure that we're all on the same page before we really begin our application lectures next week, where we will be applying some of the stuff we learned or started to introduce in lecture one to the current pandemic. So right now I will say, please, everybody just try to do question one, and in 5 minutes, we will, I'll run through the solution. And if you want this PDF file, it is available. I put it on the stream for the course, so you should be able to access it there. But if not, you can just look at the screen and work from here. So everybody just take 5 minutes to work through problem set one. Okay, maybe maybe we can. Well, if you haven't finished, don't worry. I think if you've managed to even do the first two, then you've basically got the point. If you haven't, then please do tell me, and I do encourage you to not be shy and not be self-conscious on an online course like this. There's no such thing as too silly a question for me. If anything, it shows me how brave you are about confronting the fact that you don't understand something. So please do not feel self-conscious to ask me anything, please. And I understand that for some of you, this is very basic. For some of you, this may be something that you need to get used to. And for this, practice makes perfect. So if indeed that is the case for you, please just drop me an email on my Digital Nalanda Gmail. It should be available on my email should be visible to you. If not, I will put it up. And please let me know so that I can come up with additional practice material for you. So if you now allow me to stop sharing. Okay, now what we will do, so can everybody now see my handwriting here? Is this visible?
Yes, sir.
Yes,
sir. Okay.
Your hand is visible, sir.
Thank you.
Your hand is visible, sir.
Thank you. Okay, so let's just work through these. And the first one is question 1. Okay, so what is sum I goes from 1 to 3 of I? Okay, so this notation simply means whatever expression you see in here, you just write out from I summing.
Excuse me, sir.
Yes.
Excuse me, sir. So
Yes.
your camera, I think, reverse, and we are seeing a reverse image.
You're seeing what?
Reverse image.
Inverse image.
Reverse. Yeah, inverse image from left to right. It should have been right to left. Okay, sir.
Can you see this better now? Is this still the inverse image or is this better?
Yes, sir.
Yes, sir. Now it is good, sir.
Okay, thank you. Okay. So all this is simply telling you that whatever expression you end up in here, there is some function of I. You just write out from I goes from 1 to 3 and you sum it up. Okay. So this is just 1 plus 2 plus 3. And that is 6. Okay. So that one was straightforward. The next question is the same thing, but now I squared. So that is also simply just the expression where I is equal to 1 squared plus the expression where I is equal to 2 squared plus the expression where I is equal to 3 squared. Okay, so this is 1 plus 4 plus 9, and that is 15. Okay? And so then the third question was, now I've done something, I've changed where the I begins and where the I ends. Okay, so this means I'm summing this expression for all I from -3 to 3. Okay, I mean, you could write it out, but that should be clear that is 0. Okay, why? It's because for every I am.
Sir, sorry for interruption. Sir, your voice is not properly audible.
Okay. So I think that's because of the position of the microphone. Is this better if I speak here?
Yes.
Yes, sir. But actually, what you have right, sir, it is gone top of my screen, and it's actually in this slide recording button is there, so it cannot properly see what you have written from top. But I can understand what you have written from the top. But actually, this whole what you write, it's come in whole page. That is better to understand. It is possible, sir.
I'm not sure I understood. You're asking me to. So I'm trying to. So first of all, you said my voice wasn't clear. Is my voice clear now?
Sir, yes, sir. It is clear now.
Yeah, but you're saying that what I'm writing is not visible to you.
सर एक्चुअली आप जो लिख रहे हैं वो सर जो हमारे जो स्क्रीन है, जो हमारी गूगल मीट की जो स्क्रीन है, उसमें टॉप में आपको जो आप जो भी लिख रहे हैं वो हमारे टॉप लेफ्ट में शिफ्ट हो गया। उस टॉप लेफ्ट में शिफ्ट होने की वजह से क्या है सर कि एक्चुअली उसमें हमारे यहाँ एक रिकॉर्डिंग स्टार्ट हो गई इसमें, तो रिकॉर्डिंग एक्चुअली उसमें रिकॉर्डिंग बीच में आ रहा है। तो ये आपका जो आप जो लिख रहे हैं वो क्या पूरी स्क्रीन में दिख सकता है? तो वो ज्यादा अच्छा रहेगा अगर ऐसा हो सके तो ठीक है, वरना इट इज गुड।
So you have to excuse me, my Hindi isn't perfect, but so this is being blocked. You're saying on your view. I'm trying to. I would. So if you try to make me. So let me actually shift to my face. Hang on. Let's try this. So if I do this, right, and you see me, right?
Yes, sir. It is correct.
Then you see my entire face.
Yes, sir.
You see everything, right? So when I switch to this other camera, this is now blocked. You're saying you can't see everything?
What, sir?
When I switch to the other camera,
correct,
right? You're saying that it's no longer fully visible to you. You cannot see the full
correct.
screen.
Correct.
I see. Okay. So can somebody so what do you see instead? When I switch to the other camera, can you describe what you do see? Because it should show you the full screen. Unfortunately, it should show you what I'm seeing on this camera. Let me see.
I think.
Ashish, can you rotate your cell phone? I think there is a problem of rotation. I can see visible clearly what sir is showing. On my device, it is fully visible. Just try to rotate the phone.
Sir, my laptop to join on. I join through laptop.
Okay. But we are. I can see clearly. I can see full screen. I don't know why you are not seeing. आपके शायद कुछ problem है.
Okay, then ठीक है. Sir, you please continue.
Okay, so if you are having difficulties, then just please go back to the video recording because it should be.
Yes, sir.
Okay, so I apologize that it doesn't necessarily work. So I think what happens is on your own side, you can pick how you want your own layout, and this happens to me all the time. And so sometimes you can choose to have the layout to have maybe some panel on the side where there's speakers and participants. Sometimes if you get rid of it, if you hit X on that, then the screen becomes bigger.
Now it is proper, sir. Or it is visible for me.
Okay, good. That's all. Okay. So let's no problem. Okay, so let's continue. So yeah, so the sum from I equals -1 to 3 of I is 0. That's simply because, if you just write this out, it's -3 plus 2 plus 1 plus 0, because you also have to sum I to do. And then everything that appeared here now appears, -3, -1. Everything that appears here, appears with the plus sign, and that all vanishes, right? So +1, +2, +3, this is 0. Okay, so that's the only subtle thing to remember, is that sometimes this limit, the beginning and the end doesn't have to be 1, it could be 5, it could be 0, it could be -300, okay? But this is just a very compact way of writing a sum. Okay, and then the final question, okay, so the reason we're doing this is because the next problem is going to immediately get very interesting, okay? So let's just really stress this point. Just to get used to it. So this is again just to make for practice. Okay, so practice makes perfect. So we do this. What is this? I squared. Okay. Well, that is it should be 30, right? Why? Because it's just twice this sum. Okay, it's just 2 times this guy. Okay, that should be clear because this is equal to sum I equals 1 to 3 of I squared, right? But when you square I, when you go from -3 to 0, it's the same thing, right? So it's just twice this, and then I equals 0 doesn't give you anything, so this is just 30. It's twice this. Okay, So you could have written it out and you would have calculated the same thing. Okay, so this is just to get you used to this type of notation. And now what we'll do is we will move to the next problem. Okay, so you should be seeing my screen again. Okay, and now we're getting a bit more abstract. And I hope you'll see why this is very interesting. We're about to do something very, very sophisticated with this, but now I'm going to give you about 5 minutes to work out problem two. So please work through problem two. Okay, so let's now work through these problems. So the first one is asking if we denote Sn, so this is very abstract notation now. It's saying that there's some quantity S, meaning sum really, but the sum is now indexed by this number or this abstract symbol n, which is defined as so this is defined as sum goes from little n equals 0 to 3 of x to the n. Okay. So just like before, all this means is that there is an abstract index, little n, that you're summing from 0 to 3 of this quantity. So S3, if you just write it out, is x to the 0 plus x to the 1 plus x to the 2 plus x to the 3. Okay, but no matter what x is, x to the 0 is just 1. Okay, so just 1 plus x squared plus x cubed. Okay, so that's what S3 is. Okay. The next question is, what is S0? Okay, well, S0 just means the sum goes from n equals 0, but really up to 0, so it's just the first term of x again. Well, this is just 1. Okay, it's just the first term in this. There's only one thing to sum over, which is n equals 0. Okay. The third question is, what is s to the n plus 1? Sorry, n plus 1. So the index here is n plus 1. The index here is n plus 1 minus Sn. Okay, well, let's just write this out. This is sum goes from n equals 0 to n plus 1 of xn minus sum n equals 0 to the n of xn. But recall that this is just saying that I'm summing from n equals 0 to n plus 1 of all of these guys, but I can actually write this guy as, so let me just write this out, as sum goes from n equals 0 to n of x to the n, plus the last term that I'm omitting from this sum by only summing to n. Okay, so that's this plus x to the n plus 1. This is just from the definition of what this quantity is. Okay, and then I'm subtracting Sn, S capital N, which is n equals 0 to n. S of x to the n. So this term cancels this, and it's just x to the n plus 1. Okay, so this quantity is simply x to the n plus 1. Okay, so then the final question was, maybe this is not good. The final question was, what is x times Sn plus 1 minus Sn plus 1 equals what? Okay, well, let's just write the definition again. Sn, capital N, is the sum from little n goes from 0, capital N, of x to the n. Okay. So x times Sn, which is this first term, is just sum goes from 0 to n, and I'm just multiplying this now by x, This is just x to the n plus 1. Okay? But now notice, sorry, little n plus 1. Little n. But now notice, if I go from 0 to capital N, and I take little n goes from 0 to capital N, this is the same as sum of n equals 1 to n plus 1 of x to the n. This is the same sum. It's just rewritten in a different way. Okay? If I write out all the terms in this, I will get all the terms appearing here. Okay? And that's simply just taking x and multiplying it by s of n. Okay? So if I multiply this quantity by x, this is what I get. And then this I can rewrite as this. It's the same thing. Okay? But now, if I want to let me and so the question is, what is this plus 1 minus Sn plus 1? So let me add 1. This is 1 plus x, and then I'm going to subtract Sn sub plus 1. Okay. So I've added 1, and I'm going to subtract by the definition of this quantity, but now evaluate it to n plus 1. So this is minus n equals 0, n plus 1 of x to the root 1. Okay. Now look, 1, yeah, I can also rewrite 1 as x to the 0. So I can bring, so this plus this term, because I'm summing from n now equals 1 to capital N plus 1, little n equals 1 to capital N plus 1, I can actually bring this term and rewrite it as a sum. This equals sum n equals 0 to n plus 1 of x to the n. Okay? And then I'm subtracting minus sum n equals 0, n plus 1 to the n. This is 0. Okay, so this abstract notation just got very heavy, but you see, some formal manipulations and what we've done with it, and how if you're used to these kinds of manipulation, this becomes second nature. If you're not used to these kinds of manipulation, it looks like it's really, really difficult. But every time you do something like this, don't be intimidated if you've never seen it before. Just ask yourself, what is the definition? Okay, and if you need to, and if somebody's asking you to calculate strange abstract expressions, just write it out explicitly and then see what it's supposed to equal. So my first question to the class is, was this okay? Was this straightforward, or was this tricky? Sorry, I didn't quite hear that answer. So did anybody manage to? So please don't be shy. Okay, I would rather find out that I would rather know if I'm going too fast, if I'm going too slow. So if you found this to be a bit too fast, please rewatch the lectures. I will post solution sets as well. But the statement is that just using this definition here, it's a fact that x times Sn plus 1 minus Sn plus 1 equals 0. And this all just follows from this definition. Okay. This definition implies this. Okay, so very good. So now let's go back to the problem set. Okay, let's go back to the problem set, and now let's try problem 3. Okay, so I'll give you this. I mean, either you're going to get it right away, or if you didn't understand the answers to the last question, it's going to, you're not going to, well, it's going to take a little bit more thinking. So let's just spend 3 minutes trying to solve question 3. Okay. So I hope you can see my workboard again. So let's work through this. So let me just rewrite everything just to be clear. So if I just define this funny quantity as the sum of little n goes to 0 to n of x to the n, and as per the last question, we proved that s times this quantity with n plus 1, excuse me, x times this quantity evaluated up to n plus 1 minus s evaluated this quantity up to n plus 1, this equals 0. But also if we just write out Sn plus 1, well, it's just, this quantity equals 0 to n plus 1 of x to the n. So I can write this out as this quantity, but now only evaluated to n, capital N of xn, and then the final point of the sum, the final term of the sum that this misses, which is x to the n plus 1. Okay, and this is just by definition this quantity. Okay, so we have Sn plus 1 equals S capital N plus x raised to the capital N plus 1. And if this is something we proved in the last question, then it follows straightforwardly that if I just substitute this expression into here and solve for Sn, I get x Sn plus 1 equals I'm just bringing this over to the side, Sn plus 1, but I can write out what this is. It's Sn plus x to the n plus 1. Okay, but now I can solve for Sn. Okay, so this is, if I just rearrange the terms, so 1 minus x to the n plus 1 equals Sn times 1 minus x. So therefore, Sn, so this symbol mathematically means therefore, Sn, capital N, is equal to 1 minus x to the n plus 1 divided by 1 minus x. Okay. So that's the answer to question 3. So question 4. If x is less than 1, okay, you can see this. If x is less than 1, right, then as I raise more and more powers of x, it's getting smaller and smaller and smaller. If x is 1, then I raise x to arbitrary powers, let's say x to the 100, 1 to the 100 is still 1. If x is greater than 1, this quickly becomes very, very big, and it goes to infinity. So if x is less than 1, okay, and this is what S is for some capital N. We didn't say what N is. It could be any number. Question 4 is, what is S infinity? Okay, so I'll give you 2 minutes to think about that. So by this I mean I am taking this number to be very, very big. I'm letting it go all the way to infinity. Does that even make sense? So the question is, if that makes sense, what is this sum evaluated to infinity? So you're dealing with an infinite sum now. Okay, it's an infinite sum. It's saying that this sum here, I'm summing an infinite number of terms, x raised to the nth power as n goes from 0 all the way to infinity. What is that? What is that sum? So think about it for a minute or two. Okay, so if indeed, if S, then, which let's just redefine it again, repetition never hurts. If this is the definition of this sum, then, and we figured out via the results of the previous questions that we can actually, through some manipulations, solve for it. If this is what it equals to, and if x is less than 1, then let's say x squared is less than x, and then x cubed is even smaller than x, and then so on. And then basically, if I take x to some power n plus 1, and I make this really get very, very big, this goes to 0. Okay? So therefore, this sum evaluated as n goes from 0 now to infinity is actually, it makes sense mathematically. It converges to the following value: 1 over 1 minus x. Okay, so question 5 is what is S infinity for x equals 1/2? Well, this is straightforward from this answer. S infinity is 1 over 1 minus a half. So 1 minus a half is a half. 1 over a half is 2. This is just 2. Okay, so I hope you've been able to follow this because this actually contains the resolution to an ancient paradox that people had both in ancient Greece and in China, I believe, and it was the following question. So, but by the way, what does this mean? This is saying, okay, so this is simply saying that 1/2 to the 0, which is just equal to 1. Okay, so the sum S infinity, right, where x is equal to a half. Right, this is saying that 1 plus 1/2 plus 1/2 squared, which is a quarter, plus 1/2 cubed, which is an eighth, plus 1/2 to the 4th, which is 1 over 16, all the way to infinity is equal to 2. Okay, so you may have, okay, so then therefore, if 1 plus a half plus 1/2 squared plus 1/2 to the cube, et cetera, is 2, then clearly, let me not waste paper. Then it immediately follows here from this expression that 1/2 plus a quarter plus an eighth plus 1 over 16 plus so on and so forth. These are just powers of 2, 1 over 2 to the whatever power is equal to 1. Right? Because S infinity equaled this plus 1, which was the first term, which is 1/2 to the 0. I'm just subtracting that. That was equal to 2. Right? So therefore, just these terms is equal to 1. Okay? So you may have heard of, I don't know if you ever heard of Geno's paradox, but the paradox is as follows. So in ancient Greece, a philosopher named Geno had posed the following philosophical problem. If I fired, let's say I'm a runner, let's say I'm walking from point A to point B. Zeno's paradox was, well, if I'm walking from A to B, first I cover half the distance, right? But then when I cover half the distance, in the remaining part, I still also have to first cover half the distance, fine. But then I look at what's left, and I still have to cover half the distance, and so on and so forth, right? So Zeno's paradox is if at any point between A and B, I keep walking, and at any given point, I still have half the distance left to cover, I should never get to B. Okay? But we now know that Geno was not used to thinking in terms of the sophisticated. Well, this is not even sophisticated mathematics. This is something that I hope is quite accessible to people. You can anybody who knows how to just think about numbers should be able to prove this. Is that in fact, of course, you reach B, because it turns out that the infinite sum of a half plus a quarter plus an eighth plus a 16 is 1. Okay. So that's, and by the way, this simple proof that we just did here, okay, all of the steps that led us from question 2 to the answer was done by a mathematician named Leonard Euler when he was about 8 years old in Switzerland in the 1700s. Okay, this guy's a genius, right? But now we understand it so well that we can cover it very quickly. So this is not something you're going to necessarily see in the introductory lectures again, but you will see in the more advanced modules, because infinite sums are actually quite frequent for some probability distribution functions. Okay, indeed, why is that true? Because sometimes, so you see, when we ran through examples in the class of what types of probability distribution functions one has, we thought of coins flipping. Either the coin lands heads or it lands tails. So the space of outcomes is finite. In this case of a coin, it's 2 possibilities. For a dice, it's 6. For a 6-sided dice, it's 6, right? The dice can land 1, 2, 3, 4, 5, 6. There's no more possibilities. But very often in reality, we're dealing with situations where the space of outcomes is infinite, in principle. Of course, not in practice, but in principle. One example is, let's say I'm sitting in at an octroi point. Well, they're gone now. So imagine I'm sitting at a toll booth, on the highway, and I want to know what the probability of, in a given time interval, of having 1 car go through, 2 cars go through, 5 cars go through. There is some small but finite probability that 100 cars go through in an hour. There's some small probability that 1,000 cars go through. Of course, it gets less and less likely. And so in this case, in principle, the space of possibilities, the space of outcomes, is potentially infinite. Okay, not in reality, but as a mathematical idealization. So in those cases, we're often dealing with situations where we have a probability distribution function whose outcomes. Okay, so if we have a space X of some random variable X, and there's a space and there's some space of outcomes. So what this X denotes is just the space of all possible outcomes for this random variable X. So for X is a coin, then the space of outcomes is equal to heads or tails. If X is equal to a dice, then the space of outcomes is equal to 1, 2, 3, 4, 5, 6. If X is equals to the number of cars per hour at a toll booth, okay, then the space X is 1, 2, 3, all the way to infinity. Okay, and so then a probability distribution function, probability or a PDF is an assignment assigns some number, i.e. a probability, for each outcome. Okay, so what this does is it takes some probability distribution function, takes some element of the outcome, some X, some outcome, let's call it Xi. So any elements of the outcome space I call Xi, and it gives you some number which is between 0 and 1. Why does that mean between 0 and 1? Because that's what probability means. If it's probability 0, it means it's impossible. You can't have negative probability. If the probability is 1, it means it's certain. So something is either impossible or certain or somewhere in between. And usually in a random setting, it's somewhere in between. So a probability distribution function must satisfy the property as I sum over all the outcomes as I goes from 1 to n, this has to equal 1. That's just saying all of the possible outcomes must happen with probability 1. That's just saying anything that's possible has to happen. Nothing more than that. And so sometimes this sum n can be infinity. Okay. So in the case of a dice, right, p of xi is 1/6 for every dice roll, and you sum 1/6 from I goes from 1 to 6, that's 1. Right. But in the case of the number of cars per hour at a toll booth, this probability, okay, so this number, let me refer to this. This, by the way, this is probably, there are 2 probability distribution functions you have encountered your entire life without knowing it. We saw one example in the first lecture, which was the Gaussian distribution, okay, which is this bell curve type distribution. This is everywhere. This describes, for instance, the distribution around the average of a large sample. Let's say the heights of children between the ages of 10 and 11, let's say, in some area, or the weights of adults, in some country. There's another probability distribution function that you see everywhere, which basically corresponds to this. Is if there is some average probability so if there's some event for which there's an expected average number per time interval or some spatial interval. The example used is the number of cars per hour at a toll booth. That is another probability distribution function you've been implicitly seeing your whole life, and it's called the Poisson distribution. And the Poisson distribution, this is sort of extra material, but it will come up in future modules and lessons. The Poisson distribution says the probability. So the probability of, let's say, an integer number of events, let's say number of cars passing through a toll booth at a given time, n is given by, I have to remember this actually, yes, e to the minus lambda n times lambda to the n factorial. Let me double check this. I just need to be sure. Okay, so what is this factorial notation? Again, this is bonus material. Please don't stress if this means nothing to you. I'm just advertising something that will come up. So anytime in mathematics, the notation m lambda m times m minus 1, m minus 2, all the way to 1. Oh, excuse me. This should be. Okay, let me just double check this. Just make sure I'm going from memory, so I need to. Yeah, that is correct. And there's no n. I apologize. Anyway, no need to stress over this formula. But if you just had, let's say the average, and lambda is average number of cars per, let's say, hour. Okay. So what this distribution is telling you is that if there's some average number of cars per hour, then this is, if I just were to plot this as a graph, this is something like, I don't know, something like this. Okay, where this is 1 car. This is what P as a function. That's saying you're most likely to see 1 car per hour, but then there's some finite probability that you'll see 0, and maybe you'll see 100. This process is known as a Poisson process. Okay, so this is just sort of a general advertisement for the types of things that exist in reality. But the reason I bring it up, and the only reason I brought this up, was to say that that if the Poisson.
Excuse me, sir.
Yes.
Sir.
Yes.
Sir, is this Poisson distribution is the same that we call count distribution or something?
What conditional? Did you say conditional? I didn't understand.
No, sir. Count.
How do you spell that?
Count distribute.
How do you spell that?
Oh, okay. I'll check that, and in next lecture I'll ask.
Yeah.
Okay.
So
Sorry, sir.
it could be that you've come across this with a different name, right? And it could be that you've come across this distribution with very specific values for lambda or m, if you like. I highly doubt it goes by any other name other than Poisson, because it's such a foundational probability distribution function that we give credit to the mathematician who came up with it. His name is Poisson, French guy. Funnily enough, Poisson in French means fish, so it's like some Indian guy named Masa or something. Masli, strange, but anyway. So this is the reason. The only reason I bring this up is because if the probability for a given event, if let's say the probability of finding n cars per hour is given by exponential of minus lambda, where lambda is number of cars per hour, lambda to the n over m factorial, where m factorial equals n times n minus 1 times n minus 2 all the way to 1. Then it turns out that sum m goes from 0 to infinity, p sub n equals 1. Okay, so these types of infinite sums that we're seeing, it's not obvious, by the way. This takes a little bit of extra work that in the advanced modules we will cover all of this. Okay, so I'm trying to just expose you to the concept at this point only knowing 10 standard mathematics, and then later we will build up the mathematics for people who may not already have it and cover all of this. So so what have we covered so far in this problem set? Okay, and I will post solutions so you can work through the solutions in your own time if you like. We have covered this notation, this abstract notation of sums. Okay, so the sums, let's say, and you can write it in many different ways, right? I can write the sum x to the n, little n goes from 0 to capital N. We basically tried to get used to this summation notation, right? So there's another sum which is sum of I goes from -3 to 3 of I squared, etc., etc. This is really what this problem set was trying to get used to, which is manipulating expressions like this and not being scared of them. So if you're used to them, not a problem for you. If you're not used to them, it seems like a lot. So the way to get used to them is to just practice. Okay, so I will post the problem sets and more solutions and some extra reading drawing from free resources if you want. And if you need more information, you need more resources, perhaps I didn't explain something well enough, please tell me, and I will add that to the course page. But nevertheless, in this seemingly, not so, simple, in the seemingly simple context, we've already seen some pretty advanced stuff. We've seen the possibility that sums can be infinite, okay? And that, in fact, infinite sums are often, things that we see in reality, right? So, like this Poisson process, this notion that there's a random, and by the way, this Poisson process can correspond to many things. What is the probability that a lightning will strike, on some at some point of land, over a given amount of time? What is the probability of being struck by lightning twice, 3 times, etc., etc.? This all follows a Poisson process. Plane crashes, car accidents, everything that is a random event where the individual random events are independent of each other goes by a Poisson process. So, and this is one of the superstitious things that if you understand a little bit about statistics, you know better than to be victim to. But a very common superstitious thing is someone who's just like, if there's a train accident last week, then this week somehow there's less likely to be a train accident because there's never 2 train accidents on the same piece of track, in the same month. That's never happened before, so therefore I'm safer traveling on the train today. That's not true. Okay, probabilities are independent of each other. Okay, if the outcomes are completely independent of each other, that's going to happen. So it's one of these common sort of occurrences that people, if indeed the events are completely independent of each other, they're not always independent of each other. Sometimes, in big parts of the country we have a Maoist rebellion, right? So sometimes you can get train crashes twice in the same part of the track in the same month because there's people really pissed off with the government trying to blow up the tracks, obviously. So not all events are completely random, but some are. Okay, so very good. So let's move on to so now that we've sort of worked through the first several problems, let's go back to the problem set now, and I'm going to ask you to now, hang on a second. So now we're going to leave all of this infinite sum stuff and then just go back. Oops. Why am I not? Unfortunately, it's saying I cannot share my screen anymore. It's very strange. Is Mujahid there?
Yes, sir.
Yeah. Do you have any idea why my screen sharing has stopped, or it's not letting me share my screen anymore?
Sir, I'll check, sir. 1 minute.
Okay. Nevertheless, okay. Look, even if this doesn't happen, I'll do something. Maybe you can see this. Okay, if you can read what's on the screen.
Yes, sir. Yes.
Still not allowing permission. Okay, so we have a technical issue here. I'm no longer able to share my screen, but let's. So either you can pull up the PDF from the class page on Google Classrooms, or you can just stare at what's here on the screen. So now, if you can even read this, I understand it's probably quite small. Here we go. Now I would like you to do problem 6. Problem 6 and 7, actually. You can do that. So I'll give you about 5 minutes of these.
Sir, screen is not visible.
Oh, I see. My
Yeah,
screen is not visible at all.
yeah, it's blur. Question is not
Oh,
seen
it's
properly.
not seen. Do you have but can you see can you see this okay? Is
Yes,
this
yes,
visible?
I can see.
Okay, so
Yeah.
the writing on the iPad is not visible. Okay, let me try and hold it up.
Hmm.
Otherwise, the same PDF is available on the Google. So if you just go back to the class on the Google class, I posted the problem set PDF of the problem set just before the lecture, so you can look at it yourself on your side.
This has got
Is
it.
this visible? So unfortunately, I'm not able to share my screen like I was. Let me try again. Maybe it's changed.
Yes, sir, we got a PDF from classroom.
You got the PDF.
Yes, yes, yes.
Did you get the PDF or did you?
Yes, I got a PDF.
Okay, thank you.
So we can use it.
Okay. Okay. Just maybe 1 or 2 more minutes, and I will just go through this. Okay. Yeah, I think I found what the mistake, the error was, and I could share my screen subsequently. So let me just test whether it's possible. Can everybody see my screen?
Yes, yes, it is visible.
Okay, so we're back. Okay, so very good. Okay, so let's work through this problem set. So I apologize for the small technical glitch. So if you weren't able to see the problems, it doesn't really matter. That's right. Okay, so this is again just should be straightforward manipulations of some quantities. I'm just trying to get you used to certain mathematical notation. So when we do turn to practical examples, so where is this headed? We will actually, you know, in the second module, after we've sort of completed our basic tour of the basic concept, which is what these introductory lectures are meant to do, we're going to get right into to some real practical applications. And so these kinds of things that I'm setting up now will come up again. So if you're having difficulty with them now, it's okay. You learn from practice, and so that when that moment comes, you know, we can really, solidify your understanding. But obviously, things move faster if you're able to understand them at this point. So the question is, if X is possible roles possible dice rolls, right? So it's just, it's just the dice rolling 1, 2, 3, etc. to 6. Okay, and if the probability of any number is just 1/6, it's a fair dice, then what is the sum of I goes from 1 now to 6? Really, I should have put 6 in the problem set, excuse for that. Of probability of xi times xi. So xi is just a random variable. It's the outcome of the dice, right? So if the probability for any number is 1/6, then this is just sum of I to 6. So this number is going to be a 6 for every possible roll of the dice times the actual outcome on the dice itself. Right? So xi is just whether you roll a 1, whether you roll a 2, etc., etc. So this is 1/6, 1 plus 2 plus 3 plus 4 plus 5 plus 6. And so this is 1/6. 1 plus 2 plus 3 is 6. Plus 4 is 10. Plus 11 is 21. So this is 3.5. Okay, so this is simply the statement that if you throw a dice, an infinite number of times, and you just recorded the number that you rolled, on average, you expect, and if you divide by the number of times you roll the dice, on average, that number will become 3.5. So this is the same example we covered in the lecture, but I'm just spelling it out again here, just for repetition's sake. So now the question is, what is I goes from 1 to 6? Probability of the dice roll. Okay, sorry, square. Okay, well, this is the same sum. Okay, so again, this is just 1/6 for every I. For every dice, or every outcome, it's just the same number, which is 1/6. So I can pull that out of the sum. 1/6 sum I goes from 1 to 6 of the outcome squared, which is just I squared. This is 1/6. 1 plus 4. So this is 2 squared plus 9, which is 3 squared, plus 16, which is 4 squared, plus 25, which is 5 squared, plus 36, which is 6 squared. Okay, so what is the sum? This is 10, this is 20, so that's 30, this is 55. So this is 55 plus 36 is 91. So this is 91 divided by 6. Okay, so that's saying that if you rolled the dice an infinite number of times and you recorded the outcome of the square of what you're seeing, on average, after an infinite number of times, and if you divide by the number of times that you're doing this, so if you did it like 6 times, you're dividing by 6. If you did it, 100 times, you're dividing by 100. You're going to get this number, 91 divided by 6. Okay, so now let me start sharing my screen again. Okay. Okay, now I would like you to do problem 7. Yes, I would like you to work out problem 7. So I hope I'm mindful of the time we have left, so I'll give you 3 minutes for this. Okay, let's work through the solutions. Now I don't know how you decided to approach. This is a bit blurred. Just need to focus. Quite out of focus. Give me 1 second. Just to focus the camera. Okay. Okay, so the question was, if we have some function of the random variable, it could be any function. It could be the random variable itself. It could be the random variable squared. It could be the the sign of the random variable. Who knows? Whatever function. We denote the expectation value with angle brackets. Okay, and this expectation value is just simply the weighted average. This is saying, and it's called the expectation value because it's simply telling you what you would expect for this function over all the possible outcomes of the random variable. Okay, so you could have taken the square of the dice roll. You could have taken the cube of the dice roll. The expected value of whatever function you have is just the probability of that outcome times the function evaluated on that outcome, summed over all outcomes. Okay, now these two questions that I asked, they're actually, you don't even need to do very much work to come up with a solution because of the following observation. So this is a trick. It's not really a trick. It's true. But observe that if I take any constant number, okay, so let's say some number. So that is, it is not a function of the random variable. Okay, let's say 3. Okay, what is the expected value of 3? It's just 3. Okay, or any constant, the expected value of the constant is just the constant itself. Okay, what that means is, if I just follow the definition, right? If I want to know what the expectation value of any constant is, I put in sum goes from I goes to n. Functions can be constants too, so I just put in the constant comes p of xi. Right, but this is just a constant multiplying all the different probabilities, so I can pull it outside the sum. But by definition, this has to sum to 1. So this is c times 1. It's just c. Okay. So why does that help us? Well, it makes our calculations much shorter. Note that once you calculate the average of anything, right? Let's say you calculate, once I calculate the average of x, okay, that is now, so what is the average of x? It's just summed over all the random variables from I to n. Now this is just some number. That's it. Okay? This is no longer a function of the random variable. It's just a number. Okay. So if I were to take the expectation value of this number, it's just the number itself. Okay. This looks like a lot of action for nothing, but it's important Because if I were to ask, then what is the expectation value? So if I construct number x minus the average of x, that's my random variable. Okay, so when we did the dice, the average dice roll was 3.5. So now I'm asking, what is the expectation value of the number I get on the dice minus 3.5? Okay, that's what this sort of indicates. Okay, well, if I take the expectation value of this, right, well, it's just, and expectation values are linear, by the way. That means the expectation value of some variable, plus another variable is just the sum of the expectation value. So this is just equal to the expectation value of x minus the expectation value of this constant number, which is just the expectation value of x itself. This is 0. Okay, and this is simply, and okay, by the way, this looks a little annoying. Just write it out, and you will see that this is very quickly true. If I were to ask, what is the average deviation from the mean? Okay, so mean is another word for average. Okay, I don't know why you have two different words for the average, but I think it's because of mathematics is a very international subject. Every major civilization in the world has contributed to it, particularly ours. The number system that we count in is from India. And it's very important because before in Europe, before they used decimal places and zero as a placeholder, they needed horribly complicated machines to do things that we now just do in our heads. Okay, and so the contribution of many different societies has contributed to mathematics. The Arabs, the Chinese, and in Europe, many different countries have contributed to mathematics. And so the reason we have mean as another word for average is because in French the word for average is moyenne. Moyenne also means mean. It's another translation. So there's a lot of these strange words that you see again and again with different meanings, and it's just the nature of the international nature of this subject. It's a product of humanity, okay, not any individual or any particular culture. So, what is the average deviation from the mean? This is simply asking, if I have a random variable and I know that its average is supposed to be something, what is its fluctuations around that average, right? This is a very interesting concept to construct, right? So you have a particular height. What is the average, how far are you from the average, right? So some people are above average height, some people are below average height, some people are above average weight, some people are below average weight. And if we're interested in what that average of that deviation is, of course, it's going to be 0 by definition of what average means. Okay, so if we're interested not in the average of certain quantities in a particular random sample, but we're interested in, let's say, how things tend to fluctuate from the average, okay? We want to figure out what is a useful quantity to figure out what the fluctuation from the average is. Okay, so that we realize that quickly that constructing something like this is useless. Okay, because the statistical average of this is 0. So what about this? Okay, this is known as the mean deviation square. And the problem asks you, what is the average of this quantity? Okay. And so in electrical engineering, this comes up, right? Or even if you're not an electrical engineer and you're just looking at your meter in your home for electricity, we have an alternating electric supply. Okay, that means the current goes backwards and forwards many times in a given second. I think 50 times a second, I think in India. In some countries it's 60. And what it's doing is it's pushing and pulling electrons backwards and forwards. And it's that pushing and pulling that's giving energy into all of our devices. And so if you looked at the average voltage over time, by definition, it's 0, right? Because it's an alternating current. It goes up and down, up and down. It spends as much time above 0 as it does below 0. So the concept that you'll see often in electrical engineering for alternating current is RMS, root mean squared. Okay, so this is the mean of the square, and the root is the square root of this. Okay, so it's a way of capturing deviations, fluctuations from some average value, whatever that average value is. So what is this quantity? The problem was asking you to figure this out. Okay, well, let's use all of the information that we've had before. So let me move to another page. Okay, so we were asking what is the average of x, the deviation of the random variable x from its average value squared. So remember, this is just shorthand for this quantity. Summed over all the outcomes of the probability of that event, that outcome, times whatever function you're trying to evaluate on that outcome. Okay? So this, we just expand out. Let me just expand the square. So this is x squared plus the average squared minus 2 times x times the average. Okay? But as we've seen before, anytime you just get a number, so once you have something like this, okay, once you take the expectation value of something, it no longer depends on the random variable. It's just some number. So this is just some number, and this is just some number. And so when we have just the average value of just a number, well, it just gives you back that number. So this is equal to the average value of x squared plus, I mean, this is just this number squared minus 2 times, now I have, again, just a number, so I can pull it outside, the average, 2 times this average. But now I'm taking the average of what's left inside. Okay? So this is none other than average value squared itself. So what we call this, what we call the standard, the variance, this is called the variance. This technical term for this is a very important concept. The variance is just the average of x squared minus the average squared. This is what the variance is. This quantity, variance, is just given by this expression. And the square root of the variance is known as the standard deviation. And it's a very important concept because it tells us how much our random variables are fluctuating from the average. Okay, so if we recall from, let me share my screen again. If we recall from our lecture, okay. If we recall from our lecture, here, what is the outcome if we just, you know, in this case, we took, 10,000 trials, individual trials of 1,000 consecutive coin tosses and taking the average, we see that, of course, on average, we expect to get 0.5, which is that the coin lands as often on one side as it does on the other. But, you know, for some of these, you know, but for a sufficient number of trials, we're not always going to get the idealized outcome. We're going to get some distribution. And this distribution is known as the normal distribution. And these fluctuations away from the mean are captured by this quantity, the standard deviation, which in this case for 10 million coin tosses is about, or 10,000 trials of 1,000 coin tosses is going to give us a standard deviation. Typically the fluctuations are going to be 0.0158 away from the expected mean. So that's what the standard deviation is. Okay. So now I think I'm mindful of how much time we have left. So maybe let's go back to the let me reshare my screen again. So we'll maybe work through the last problems in a bunch, and give you 5 minutes to work through them, and then we'll run to the solution. So please work through problems 7 and 8. Don't worry about 8 so much. Just work through problem 7. So I'll give you maybe 3 minutes for that. Okay, so let's work through that solution. So okay, so the concept of likelihood is crucial. It is very, very key. It will come up again and again and again, and especially if we move on to real life applications, particularly if you're interested in machine learning later, which is something that we also hope to introduce in the school. So likelihood is different, is related to probability. Okay, so if I have a probability of a random event occurring, but that depends on some parameter, let's say theta. Okay, so probabilities can be parameterized. Okay, so imagine I have a way of controlling whether a coin is fair or not by adding weights to one side or another, or same with dice. Okay, then then the probability of obtaining a heads is a function of some parameter. This is all that this is saying. So the probability of obtaining a dice, let's say probability of obtaining a heads, is theta, and then because probabilities have to sum to 1, then the probability of obtaining tails is 1 minus theta. The likelihood function is simply the probability, the likelihood the likelihood function is the same quantity, or relates to the same quantity, but no longer viewing the outcomes as a function of the parameter, but by viewing the parameter as a function of the outcome. So it's reversing the sense in which we mean what this means. So the likelihood of a given outcome, okay, and that's a function of theta in this case, is the probability of obtaining all of the different events that we had. So what is the probability of obtaining heads, heads, tails, heads, tails, heads, heads, tails? What is the probability of this? If the probability of obtaining a heads is theta, and the probability of obtaining tails is 1 minus theta. So because every time you flip a coin, it's independent of the time you flipped before, then the probabilities are simply the products, the probability of obtaining the sequence of events is simply the product of the probability. So if we have 1, 2, 3, 4, 5 heads, 1, 2, 3, 4, 5. Did I have one more? Yep. No. It's this is equal to the probability of obtaining heads to the 5th power. It's 5 heads times the probability of obtaining tails 3 times. Okay. And similarly, if we just keep going, if we now just add to the same sequence of events, heads, heads, tails, heads, tails, heads, heads, tails, tails, this is just one more occurrence of tails to the previous outcome. So that's theta to the 5, 1 minus theta to the 4th, and then probability. The final question was heads, heads, tails, heads. It's the same outcome, but then the subsequent coin flip gives tails. So that's just, again, 5 occurrences of heads and 5 occurrences of tails. So question 8, okay, so question 8 is, so these are likelihoods. Okay, this is saying this is the probability. The likelihood is a probability of obtaining this outcome, right? Or this outcome, or this outcome. So for each of these, the question is, what value of theta maximizes the likelihood? Okay, so that's simply asking, if you observe a given outcome and you know no other information, what is the likeliest value for this unknown parameter that would have given you that outcome? Okay, so what this is asking you to do is to look at what this function looks like as a function of theta and pick the maximum value. So let's do that. Okay, so let me just share my screen and let's actually do that. Okay, so let me see. So yes, can you see my screen? Okay, so I'm just going to, just for the sake of showing you, so this, I put a link up to this website for those of you who are interested. It's relatively straightforward to get used to if you've never seen it before, but it's basically an online scientific calculator. So if I wanted to plot some function, okay, so I wanted to plot what is, let me call theta t. So t to the 5th, so this is for the first, so what I'm doing now is I'm just seeing what is the maximum likelihood that maximizes this outcome of obtaining 5 heads and 3 tails. So that means I want to plot theta, so I'm just calling theta t to the 5th, 1 minus t to the cubed, and I'm interested in all values from t goes from 0 to 1. Okay, you see here that the likelihood is maximized by some number, which is actually greater than 0.5. In fact, it's 0.6. Okay, a little over 0.6. So the maximum value, so the likeliest value for theta so if you have seen the outcome of 5 heads and 3 tails and you had no other information, then you are going to conclude that the likeliest outcome is that the coin is unfair. Okay, that the likeliest value for what that coin is a little over 0.6. But the next question was, what happens then if we subsequently flip one more tail? Okay, so that means now we have one more occurrence of the tail. What does that function look like? And as you see, this is now it's starting to get a little bit away. It's starting to get closer to 0.5, right? And so you see where this is going, right? So then if we flip one more tail, then it's telling you that the likelihood is maximized for a perfectly fair coin. Okay, and so this is typically what happens in real life. Okay, is that if statistical inference, data science, is about understanding what the underlying process is behind, well, one of the aspects of data science is trying to understand what the underlying process corresponding to the observed set of events is. Okay, so in the next lecture, we will be applying this to, let's say, the epidemic. Okay, so what is the likeliest value for this? Maybe you've heard of this number, the R number, how much the virus is reproducing given the data that we're seeing. These are central questions to statistical inference. And so the way these are done is that people look at the observed outcome, and they have a model that could have produced it up to some parameters, and then they tune those parameters such that it fits what is observed to the likeliest. It fits, it decides that, well, the thing that maximizes the likelihood is probably the value of that parameter. And as we've seen in these examples, that with a small number of data points, you can get an answer that you may not be very confident about. But as you take more and more data points, things will, of course, converge to the expected outcome. So there's a few more questions left. I think these questions 9, 10, and 11 should be quite straightforward. But it's to introduce the concept of conditional probability. Okay, so the idea that every time you flip a coin, the next time I flip the coin, it doesn't matter what happened before. And this is a statement that these are independent probabilities. The probability of me obtaining a heads at a given coin flip does not care about my previous coin flip. It doesn't care. So they're independent probabilities. But not all probabilities are independent. And we know this from dealing with cards. Okay? Every time you play a card, right, that's one less card in the deck. So the next probability of obtaining, let's say, 2 consecutive queens is not the same thing as, obtaining a probability of a queen twice. But they would be independent if you had 2 separate decks. Okay, and so the way we denote conditional probability is that if probabilities are independent, then the probability of seeing outcome X and outcome Y, 2 completely separate probabilities, random variables, is just the product of the probabilities. But if they're not independent, then it's a little bit more complicated. And all of this is simply a definition. It's saying that if the probabilities are conditional, then the probability of obtaining an X given the outcome Y is denoted by this quantity. So if you're going to see both X and Y, then it must be equal to the probability of seeing X given that Y has happened times the probability that Y has happened, or vice versa, right? It's also equal to the probability of obtaining Y given X times the probability of Y. And so setting these 2 terms equal to each other and just dividing through is known as Bayes' theorem. And although it may not look like very much here, it actually allows us to completely reinterpret what we mean by how we think of probability. And it allows us to go from this frequency type interpretation to a hypothesis testing type interpretation. And that's what we're going to cover. We're going to begin with this in the next lecture. So this is all we have time for today. So let me stop sharing. And if you have any questions, please please feel free to ask. But this formally concludes our problem session for the day. And on Monday, we'll resume our lectures again. And next week, we'll resume our usual schedule of Monday lectures and Friday question and answer session. So does anybody have any questions about what we covered today? Please ask away. Feel free to ask. Otherwise, you can also ask me over email. I may not respond right away because I have lots of emails to answer typically on a given day, but I will do my best. If any of this was unclear to you, please let me know over email. It's important for me to know that. And I can try and find more material to help you with this, or pace my lectures differently. And Ramiz will do the same. Okay, good. I have another meeting and I have to go now. So thank you everyone for today, and I'll see you on Monday.
Thank you, sir.
Thanks.
Thank you, sir.
Bye everyone.